going to look. There's one branch. The other point, negative 1, is going to become the point 0, 1. And here's the other branch. Because, of course, I didn't put it in here, that you do have a horizontal asymptote, right, that you never moved. Okay. If we're graphing a cube root, then just going to go over this quickly. A cube root graph is going to look like a cubed graph flipped over because it's an inverse. It's defined for all reals, and the range is all reals. So just give it a little bit of space on your window. Okay, if you have to find solutions and pay attention to how many decimal places, then you're setting these equal to each other and finding where they intersect. That is, where does cos x equal x? Well, graph cos x in your equation editor is y1, graph 1 in your equation editor for y2. And you're going to see your cos graph doing this, and the line y equals, oh, sorry, that's not a 1. It's an x. And then you're graphing the line y equals x, and then you need to see where they intersect. Okay, so our window. I want to see a cycle. I'm going to look at 2 cycles of cos. So from negative 2 pi to positive 2 pi. And I'm going to make sure that I can see from negative 5 to positive 5, although I know that my cos graph goes from 1 to negative 1. My y equals x can just keep on going, so that should show you everything. You're looking for the intersection, so using your calculate menu, you should be finding that intersection when x is equal to 0.74. Of course, at that point, y is also equal to 0.74 because you've got the equation y equals x for your second. Okay, so some fun homework for you to start on right here, and we'll talk again later. Bye-bye. New functions from old functions. We're going to be looking at adding functions, subtracting them, multiplying them, dividing them, and then more importantly, we're going to be looking later on in this lesson at composing them. So let's start with what I think are the easy things. That is, what happens when we add 2 functions together. So this is very theoretical. F plus g at x means you've got function f plus function g. The domain will have to be the domain that works for both of the functions. We'll do a couple of examples in a moment. So we'll also be looking at the same thing is true when you're subtracting 2 functions. Note the domain, multiplying 2 functions, and dividing 2 functions. When you're dividing 2 functions, you have, yes, this intersection of the 2 domains, also the restriction that, of course, your denominator can't be 0. Okay, so this here, not allowed to equal 0. The little symbol that you're seeing there, this one, is a symbol for intersection. It means that it has to be, we're looking at the x values in the domain of A that are also in the domain of B. And if they're in A but not B, in B but not A, you can't use them. Everybody got to be happy. Okay, so here's a little example of that. If f at x is root x, and g at x is root 4 minus x squared, then what would be the domain? Okay, so let's start by looking at the domain for f at x. So for f at x, my domain would be, of course, x bigger than equal to 0. For g at x, then my domain would be whatever is underneath the root, that is the 4 minus x squared. That has to be a positive number, greater than equal to 0. That is, 4 has to be bigger than or equal to x squared. And if I took the square root of both sides, of course, I would get x is equal to plus or minus 2. Of course, if it's negative 2, it works because I get a square root of 0. If it's positive 2, it works because I get a square root of 0. But what about in between negative 2 and positive 2? Well, let's test the interval. A point in between negative 2 and positive 2 would be 0. And if I put 0 into underneath the root here for my x squared, I'd get 4 minus 0 squared, and I could take the square root of that. So check, that part works. What if I go to the right of 2? Choose a number bigger than 2. If I substitute in a number that's bigger than 2 underneath the root, like a number like 3, then I would get 4 minus 9, and it wouldn't work because I would be taking the square root of a negative. Try it again for a number on the other side of this domain. That is, if you tried it for negative 3 and put it in, you're going to find again that it doesn't work. So the domain for this function then is going to be x has to actually be in between negative 2 and positive 2. How do I say that? In Math 11, I guess we would have said this: negative 2 less than equal to x less than equal to 2. How am I going to say that in calculus? Well, first of all, I'm going to erase a bunch of stuff here so I can get some space. The way I'm going to say it now is I'm going to say square bracket negative 2 comma positive 2 square bracket. And that means all the values in between negative 2 and positive 2, and the square bracket means including the endpoints. Okay, so you can see we've got 2 domain restrictions, and let me write this other one. X greater than 2, and I'll write it in interval notation, and then we'll look at what happens when I combine the functions. How do I get the domains? All right, you can see I still didn't find the big eraser, did I? Okay. So for root x, then we would be saying that so for f at x, we would be saying our domain is from 0. We said x's have to be greater than 0, from 0 to infinity. Just a little note, infinity isn't a number, you can't contain it. You always put a round bracket on infinity. Okay, so let's do a number line again and look at where these domains overlap. So here is my domain for f at x. It starts, it starts here at 0. Let's put in the negative 2 and the positive 2. Okay, so if I'm looking at the domain for f at x, includes 0 and everything bigger. If I look at the domain for g at x, then it's going including negative 2 all the way up to and including positive 2. Where does everything overlap? What makes everybody happy? Well, everybody's happy at 0 all the way up to and including positive 2. So we would call that the domain for our combined function. So the domain for f plus g would go just from 0 to 2. It would include both of them. The same is going to be true for f minus g. I'm going to write the domain here. from 0 to 2, from 0 to 2. F times g, the domain is going to be from 0 to 2. For f divided by g, then remember that you cannot have a 0 in your denominator. So when I have f over g, and let's just write out what that is. F divided by g means I've got, oh, sorry, wrong one. Means that I've got, so f over g at x means I've got root x divided by root 4 minus x squared. And our domain when we're dividing means we can't have a denominator of 0. So what values in this domain from 0 to 2 make that denominator 0? Well, of course, if x is 2, we get 4 minus 4 in the denominator, and no can do. Okay, so my domain for f divided by g is I can include the 0, but I can't include the 2, so a round bracket there. So my domain, old way of thinking about this, would be 0 less than equal to x less than 2. Okay, find the following and give the domain. So what was f plus g? Well, f plus g is simply root x plus root 4 minus x squared. What is f minus g? Root x subtract g, 4 minus x squared. What is f times g? F times g is root x times root 4 minus x squared. Or you could be writing it this way. You're multiplying a root times a root. I guess that's 4x minus x cubed. Okay, so let's stop it. Let's look at how we can do this on our graph. Okay, we can graph these two functions using graphical addition. And the way you would do that, if we're taking f at x plus g at x, and I'm using the functions above, that is, and we're using f at x, which is root x, plus g at x, which is root 4 minus x squared. So we're going to graph the sum of the two functions. In fact, we can do this graphically just by adding the y coordinates for the corresponding x coordinates. Okay, so let's graph our first function, root x. So root x, of course, starts at 0, 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. And our root function looks like this. G at x, if you recall, is the equation of a semicircle with a radius of 2, centered at the origin. So it looks kind of like that. If we are going to add these two together, we should remember that our domain is from 0 to 2. So my graph can start here and end here in both of them, because after that, it's not defined for either one or the other. Okay, so because of my domain restriction, oopsie, let me put some of this back. I get to go all the way to the x value of 2, which means the y value would be square root of 2. And my domain, I only get to start at a value of 0. Okay, so there are my two functions on their restricted domain. How can I add them together? So adding them together means that I'm taking my y value for root x, which is 0, and my y value for root 4 minus x squared, which is 2, and I add 0 plus 2, and I get 2. Let's go to the endpoint. When x is 2, f at x is 0, and g at x is root 2. Add those together, and I'm going to get root 2. When x is 1, f at x is 1, plus g at x is root 3. Add those together, and I'm estimating here, and you get the idea. You could do this with all the points. That green graph would be the sum of those two functions. Okay, now we're getting into the details of this lesson, which is composition. So you remember, I'm hoping, from Math 11 and 12, what function composition looks like. F composed of g, and we use this little symbol, and it means that we are substituting g of x into f at x. So if f at x is x squared and g of x is x minus 3, then f composed of g would be x squared acting on x minus 3. That is, f acting on g of x. So f would act on, and function composition is substitution. So when you see a g of x, put in what g of x is. It's x minus 3. So what does f do to its input? Well, whatever you put into the f machine gets squared. What am I putting in? I'm putting in x minus 3. So that means that the x minus 3 will get squared. F composed of g, x minus 3 all squared. The domain for my composite function is going to be all real numbers. Negative infinity to positive infinity. Okay, so g composed of f. G acts on x squared. What does g do to its input? Whatever you put in, you subtract 3 from it. So x squared minus 3. So when you're looking at what the domain for this function is, you have to start here and say, are there any restrictions on x squared? None. It's a polynomial parabola. All real numbers is the domain. Here's my final composite function. Also no restrictions. So the domain for this function, once again, all real numbers. And you can see that once again we're writing that in interval notation. Okay, this can get more complicated when you do have restricted domains. So if f at x is root x and g of x is 2 minus x, then let's start by looking at domain restrictions on each of these functions. Before we begin, it will help us when we start composing. Okay, so f at x has these domain restrictions. The domain restrictions would be x has to be greater than 0, greater than or equal to 0, as in you're going from 0 to infinity. 2 minus x, okay, let me just do a little bit of space here. The square root of 2 minus x. Domain restrictions would be 2 minus x has to be bigger than or equal to 0. Add x to both sides. 2 is bigger than or equal to x. You might be saying it this way. X is less than or equal to 2. I think this looks easier on interval notation. So x can be a small number. Like actually it can go all the way to negative infinity. It goes up to and including 2. So I want the 2's that are smaller than x. Okay, so there's my domain restrictions for g of x. Let me use a different color for g of x. So for g of x, here's my domain from round bracket negative infinity up to 2 square bracket. Okay, what happens when we start composing those functions though? So if I have f composed of g, then f is acting on g the square root of 2 minus x. So now that I've put this square root 2 minus x in, I have a domain restriction that my x has to be less than or equal to 2. Okay, what does f do to its input? Well, it takes the square root of its input. What are you putting in? You're putting in the square root of 2 minus x. And if you didn't know this, when you take the square root of the square root, what you're really doing is taking the fourth root. And it looks like I still have the same domain restrictions because it's an even root. And so my final domain restrictions end up being exactly the one that I started with. My domain restrictions here would be from negative infinity to positive 2. Okay, what about if I'm looking at G composed of F? So G acting on F at X. Well, F at X is root X. And so right away I have domain restrictions. My domain restriction is if I'm taking the square root of x, x has to be bigger than or equal to 0. Okay, so then what does G do to its input? Well, G takes the square root of 2 minus whatever you put into it. What did you put into it? Root x. So my G composed of F is the square root of 2 minus the square root of x. Okay, I've got one domain restriction already. In fact, I have another domain restriction right here because what's underneath the root right here has to be greater than 0. So to express those domain restrictions, I would be taking this 2 minus root x and making sure that it's bigger than 0. Add root x to both sides. How do I get rid of that root? I square both sides. 4 has to be bigger than or equal to x. So what's my domain restriction? Well, x has to be bigger than 0 and less than 4. Both of those conditions must be satisfied for the domain of this function. So my domain for the entire function, let me use black for this because I'm talking about that G composed of F, it's going to start at 0, end at 4. Okay, F composed of F. F composed of F means F acts on F at X. Remember, composition is substitution. What's F at X? It's root X. So if I take, what does F do to its input? It takes the square root of its input. What am I putting in? Root X. So that would just be the fourth root of X. And I think we know the domain restriction for this, 0 to infinity. Okay, G composed of G then would be G acting on G of X. What is G of X? Well, it is the square root of 2 minus x. Okay, that has domain restrictions already. What are the domain restrictions there? We already talked about them. It was x has to be less than equal to 2. Okay, what does G do to its input? Well, it takes the square root of 2 minus whatever you put in. And what you put in was the square root of 2 minus x. Whew. Okay, so I have the domain restriction here because of this expression. Now I still have more domain restrictions because of this root. Whatever is under this root has to also be positive. So that means that the 2 minus the square root of 2 minus x has to be bigger than or equal to 0. So let's add the square root of 2 minus x to both sides. Let's square both sides. Ooh, let's subtract 2 from both sides. And let's not make silly signs with negatives. If I multiply both sides by -1, I get -2, reverse the inequality, less than equal to x. Okay, so now combining both of these domain restrictions. This one says my x has to be bigger than -2. The first one says my x has to be less than +2 and bigger than -2. Can you see what the combined domain would be? It is saying your final domain for this function, domain for g composed of g, is stuck in between -2 and +2. That is, my x's are bigger than -2 and smaller than +2. Right, so now we get into probably the most complicated example here. We're looking at f composed of g composed of h, and it's given us the 3 functions. You should be able to see those on your note printout. I'm going to zoom this in and you'll probably not see them anymore, so keep it in front of you. So what is f composed of g composed of h? F acts on g, but g is acting on h of x. Okay, so we're going to work this from the inside out. F acts on g, which is acting on h of x, which is x plus 3. No domain restrictions on x plus 3. Linear equation defined for all reals. Good. So, working from the inside out, f is acting on g of x plus 3. What does g do to its input? It raises it to the power of 10. What are you putting in? You're putting in x plus 3. So that means I'm going to get f acting on x plus 3 to the power of 10. So once again, x plus 3 to the power of 10 defined for all real numbers. No problems yet. Then what does f do to its input? Well, f takes its input and puts it on the top and then on the bottom plus 1. What am I putting into this function? X plus 3 to the power of 10. X plus 3 to the power of 10. Can you see that I would never be able to make that denominator 0? Because raising something to the power of 10, it will always be positive. The domain for this function, in fact, is all reals, negative infinity to positive infinity. Go get a lot of practice on function composition. The concept constantly come up. Really important idea.